Good afternoon. We will begin today a series of lectures in which we will learn how to establish the convergence or divergence of a series under some conditions. The problem of establishing this property of whether a series converges or not, it can be quite difficult in general. But for a large class of series that follow certain hypotheses, things are much more straightforward. But this is the key thing. From this point on, when we learn these properties, be aware that they only work under certain conditions. So that means the series needs to satisfy certain properties. And then often these tests, these so-called convergence or divergence tests, will say something very precise. For, if something happens, then something else happens. But make the effort to not basically fill in the blanks, essentially. So to assume that the test or the property states more than what it states. So the integral test is one of the straightforward tests that can be used in some conditions to figure out if a series converges or not. And we actually alluded to it a little bit when we talked about in the previous lecture why the summation from 1 to infinity of 1 over n, so this famous series, why does this diverge? So this is a divergent series. And so I alluded basically to the integral test when I showed you an argument basically using a Riemann sum and the integral of 1 over x. So today we're going to formalize what this test implies, or what it says actually. So given a series with positive terms, so an positive and also an decreasing, so you need basically a series with positive terms and decreasing. Suppose we consider the function associated with the sequence that forms this infinite sum, this series. So you look at the term an, and then you treat that as a function of n, and that in terms gives you a function in a real number x in general. So for example, in the example here on the top of the page, f of n will be 1 over n, right? Because that's the generic term that is in the infinite sum. And suppose this associated function to this series is positive, is going to be positive, obviously, because an is positive, decreasing, and continuous. So for this test, we need all three properties. We're not going to prove, by the way, this property. I'm just going to intuitively show you how it works. But always remember the conditions in the theorem, basically. So the associated function, suppose is positive, decreasing, and continuous. Then what we call the integral test states that if the integral from 1 to infinity of f of x dx is convergent, then the series associated to this function is convergent. And it will also tell you the divergence. So it will say the same thing if the improper integral is divergent. So if the improper integral from 1 to infinity of f of x dx is divergent, then the associated series, well, the series that gave you the function itself, is divergent. So the way the improper integral is, so is the infinite series. You can state this in a more general setting. I'm going to make some comment toward the end of the lesson here. Remember, the starting point doesn't really matter. It doesn't have to be 1. So you could have a summation from k to infinity, in which case, in the integral test, you will take the integral from k to infinity. That really doesn't matter, the starting point. It's really the behavior at infinity, right? That what makes this improper integral, whether it converges or not. And I'll comment on this a little bit later, but you could think of it as a general rule. When you look at the convergence of a series, what matters is what happens in the long run from a certain point, from a certain term in the summation all the way to infinity. If you disregard or remove the first couple of terms, 1, 2, 3, however many, that doesn't affect the convergence. Again, it's the infinite sum starting from a point in the sequence that decides what whether the series converges or not. And this is because limit properties. It's nothing mysterious. You'll see what I'm talking about immediately. But let's go back to the integral test and how it applies. So it's very straightforward. Basically, if I gave you a series, so let's start with an example. Let's say you have summation from 1 to infinity 1 over n squared. You look at the function associated to the sequence that is summed up in the series. So remember, don't confuse the infinite sum with a sequence, right? So the infinite sum is adding all the terms of a sequence, essentially, right? So you always have a sequence associated to a series, and the function in question here in the integral test is the function that is associated to the sequence, which makes the infinite sum, the series itself. So if f of n is equal to 1 over n squared, in general, f of x, where x denotes a real number now, is 1 over x squared. So if you suspect that it's not a big deal to compute the integral from 1 to infinity, well, first of all, let's see if the properties required in the theorem are satisfied. So is 1 over x squared positive? Yes, because again, since n is from 1, 2, 3, and so on, we're going to consider x to be greater than or equal to 1. We don't care about this function for x less than 1. It is obviously decreasing, so also it is obviously positive, so 1 over x squared is positive. It is obviously decreasing. Sometimes you need to check to see if it's decreasing or not, but here obviously if I increase, if x gets bigger, 1 over x squared gets smaller. Now, if it's not clear whether it's decreasing or not, you could check it by various means. So, you could, for instance, so let's see, how do you check to see if it's decreasing, if it's not obvious? Well, if it's differentiable, you can take a derivative and see if it's negative. So on the integral, on the domain 1 to infinity. So 1 over x squared prime will be minus 2 x to the minus 3, which will be obviously negative if x is greater than 1. Or you could check to see if it's decreasing by simply comparing f of x plus 1, which is 1 over x plus 1 squared, with f of x and see if it's less than that, right? So if you increase x, you should end up with a smaller value for the function. And this inequality is obvious because, again, increasing the denominator makes the fraction get smaller if you have a constant on the top. So I'll get to a point in which you will actually have to check to see if it's decreasing, if it's not obvious. But if it's obvious, just state that the function is decreasing so you can show that you are aware of this extra condition. But beyond that, you don't have to write anything else. So let's go back to the integral test. We compute the integral from 1 to infinity of 1 over x squared dx. And this is just the power rule, x to the minus 2. And this gives me x to the minus 2 plus 1 over minus 2 plus 1 between 1 and infinity. Remember, when I say between 1 and infinity, when you plug in, quote unquote, plug in infinity, you really mean taking the limit as x goes to infinity of the function itself. So this will be minus x to the negative 1. And then minus, now plug in 1. Right, so minus 1 to the negative 1, which is just minus 1. And then with the other minus, that's going to be 1. And this is going to be plus limit as x goes to infinity, minus 1 over x. So that's 1 over infinity, or minus 1 over infinity, which goes to 0. So the overall limit is 1. And now the integral test says, now we apply the integral test basically. Since the integral from 1 to infinity of 1 over x squared dx is convergent, we just concluded that the limit is 1. I'm sorry, the integral is 1, then by the integral test, the summation from 1 to infinity of 1 over n squared is also convergent. Now, one important remark, that does not mean the summation is 1. Right? So that's not going to be equal to the value of the improper integral. The improper integral simply gives you the answer whether it's convergent or not. The actual value of the improper integral has nothing to do with the value of the infinite sum. So in fact, if you enter this in Maple or something similar, you'll see that this infinite sum, 1 plus 1 over 1 squared plus dot 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 1 over n squared, this is actually pi squared over 6. To see actually why that's the case, you would need to learn things like Fourier series in partial differential equations. But anyway, the value of this summation has nothing to do with value of the improper integral. So on the next page, I'm going to actually illustrate why the integral test is true, and then finish up with some other examples. So stay tuned. All right, so take a moment, pause and take a moment to write this down, these two graphs. They're essentially the same thing. The function f of x, suppose it looks like that. Remember, positive, decreasing from 1 to infinity, and continuous. So I think I forgot to mention on the previous page, all of these three properties only need to hold from 1 to infinity, you know, from over the range where you take this summation. Because remember, that's how you take the function, right? You take a n to be f of n. So you really care about the range corresponding to the starting of the summation, in this case from 1 to infinity. But remember, it can be any positive number, any positive natural number. So again, think in terms of approximating the integral from 1 to infinity of f of x dx via some Riemann sums. So the points, the index in the sequence, 1, 2, 3, n, and so on, form a partition on the interval 1 infinity. And imagine that on one hand, you could take, when you try to approximate the integral, say you take the right endpoints when you raise the perpendicular. Right, because you can pick any point on each segment on the partition and raise the perpendicular to form those approximating rectangles. If I keep on using the right endpoint, I form a Riemann sum that approximates the integral from below. So notice here, if I raise perpendiculars always over the right endpoint, so 2 for the interval 1, 2, 3 for the interval 2, 3, and so on, I always approximate the integral by from below. So the height of this first rectangle will be f of 2, right? So over here, let's write it here. So this will be f of 2, and this will be f of 3, and so on. But remember, f of 2 is going to be a2, f of 3 is going to be a3, and so on. So the actual elements in the Riemann sum are the elements in the sequence that come up in that infinite sum. So from the left picture here, I can conclude that a2, right, the area a2 times 1, right, the area of the first rectangle, plus 1 times a3, plus 1 times a4, plus all the way up to 1 times an, is going to be an underestimation of the improper integral. So the infinite sum, but starting from a2, let's write it one more time, is less than the integral from 1 to infinity of f of x dx. On the right hand side, if instead I'm going to use the left endpoints, I'm gonna obtain basically some rectangles that approximate the integral from above. So I raise the perpendicular over 1, and I come up with this rectangle, and then over 2, then over 3, and so on. This will be n plus 1 and keep on going. The height of the first rectangle again will be a1, which is f of 1. The height of the second one will be a2, and so on all the way down towards 0. By the way, remember an goes to 0, right? Ask yourself, how do I know that? Remember the divergence test. Okay, so if an doesn't go to 0, then it will be divergent, so you wouldn't bother with any other tests. So if we add up these these rectangles, these areas, these rectangles, again, we obtain an overestimation of the improper integral. So it's going to be 1 times a1 plus 1 times a2, the area of the second rectangle, all the way up to 1 times an, and so on. So this will be less than a1 plus a2 plus ... an. So this is the inequality that actually gives you everything, basically, because let's think about the two versions of what the integral test implies. If the integral from 1 to infinity of f of x dx is convergent, so that means it's a positive number, because the function is positive, right? So imagine you have a positive number. Well, if I look at the left side of this inequality, stands the reason that the summation from 2 to infinity of an is also convergent, because that quantity is less than it's positive on one hand. All these quantities are positives, remember, this is important. These are series with positive terms. So that infinite sum is squeezed between a positive number and 0, right? So therefore, it has to be convergent. It can go to infinity, roughly speaking. Now, you may say, well, hold on a second, but your original series started from 1. It doesn't really matter. If this is convergent, the fact that you add to it another term, an, which is positive, just to make it the summation from 1 to infinity, changes nothing. That means this is also convergent. If you remove from a convergent series a finite number, or you add a finite number, the situation is the same. It's still convergent. Think of it in terms of limits, because remember, an infinite sum is a limit. If the limit exists and you add a finite number to it, then of course you obtain also a finite number. So with that in mind, what about the divergent case? Well, if the integral from 1 to infinity of f of x dx is divergent, well, I'm going to look then at the right side of the inequality. Associate divergent with the word infinity here, because again, this is a positive function. So what can you say about an infinite sum that is greater than an infinite number, right? It must be infinite as well. So it must be divergent as well. You cannot have a finite number greater than a quantity that goes to infinity. So in general, we don't prove these tests in this class. We just worry about how we apply them for various problems. But I want to go over proofs sometimes like this one, at least briefly, because it will help you to understand other properties later, like for example, comparison tests. So this idea of, if you have positive quantities and, you have an inequality less than a finite number, then of course the left side has to be finite number. And conversely, or on the flip side, if you want, have a quantity greater than something that goes to infinity, intuitively it should make sense that that quantity greater than infinity must be infinity as well, or more formally the word divergent that we use here. I like to use sometimes the word infinity instead of divergent, which is kind of an abuse of the word, of the language, but because it helps with the intuitive understanding of these properties. So we're going to finish up with a couple of other examples, so stay tuned for the next page. All right, so perhaps the most important, so one of the most important segues from the integral test is the ability to establish the convergence of a class of important series, the so-called P-series. So P series is just, it's a series of the form summation from 1 to infinity of 1 over n to the power p, where p is just any real number. Well, maybe except, well, they are any real number, really. I mean, p equals 0, it's like a trivial case because it's summation of 1, right? So if p equals 0, then you have summation of 1 over n to the 0, which is summation of 1, which of course is divergent, right? Remember, if the the sequence that you sum up from 1 to infinity doesn't go to 0, by the divergence test, it has to be divergent. So P series, because we denote this by a natural number. Now, make sure you do not confuse it with the geometric series, which is something like this. Let's say 1 over 2 to the n. When the powers increase, let's say 1 plus 1 over 2 plus 1 over 2 squared plus 1 over 2 third and so on. P series have the exponent the same. So for example, P2, when you have P equal 2, we had the series from previous page, right? 1 plus 1 over 2 squared plus 1 over 3 squared, 4 squared, and so on. The exponent doesn't increase. If p equals 3, then the summation will be 1 of plus 1 over 2 thirds plus 1 over 3 thirds, 1 over n thirds, and so on. So make sure you don't confuse it with the P series. In general, it's a complicated endeavor to know if it converges, what the summation is, unlike the geometric series for which we have a nice formula in case it converges. So the integral test can establish rather quickly whether the P series converges or not. So let's just do it. First of all, notice that 1 over n to the power p is decreasing, positive, and the associated function, which is 1 over x to the p, is continuous. So to figure out the convergence of the P series, all I have to do is to do the integral from 1 to infinity, which just entails the power rule. And look carefully here, we're going to have to take a case separately, because when I do the power rule for x to the minus p, the integral is x to the minus p plus 1 over minus p plus 1, but only if p is not equal to 1, because otherwise you would divide by 0. So I'll have to take the case p equal to 1 separately, right? Because in that case it's not the power rule, although it's a case we encountered before. So p not equal to 1, and now let's plug in 1 in infinity, and in other words, let's take the limit as x goes to infinity of x to the 1 minus p over 1 minus p, and then minus, now we plug in 1 to the 1 minus p over 1 minus p. Now, if you look carefully, so let's clean this up a little bit. The convergence is boiled down to what that limit is, right? And then, because that limit is going to be then minus 1 over 1 minus p. But, you know, if the limit is finite, then of course the integral is finite and it'll be convergent. So it boils down to this limit of x to the 1 minus p. Remember, p is just a real number, not equal to 1. And as it turns out, the limit here, if you remember what the limit is of when x is raised to a certain power, the limit is going to be a finite number if 1 minus p is negative, because otherwise it will be infinity. So if you want quick examples, let's say you have x to the 1/2, x to the 3, x to the 1 over 5. As long as this exponent is positive, then the limit is infinity. So that'll be divergent. So you have two cases basically. Infinity, if 1 minus p is greater than 0. Remember, p equals 1 is treated separately. And if 1 minus p is negative, the limit will be 0. Because if it's negative, it will be like 1 over infinity. So for example, if you have x to the minus 3, that's like 1 over x third. It'll go to 0 if you have a negative exponent. So we concluded, therefore, that the summation from 1 to infinity of 1 over n to the power p is convergent if 1 minus p is less than 0, which is to say p greater than 1. And let's see what happens if p is equal to 1, right? So of course, if p is less than 1, is going to be divergent. If the other way around, this one. If p is less than 1, so summation from 1 to infinity, 1 over n to the power p is going to be divergent if 1 minus p is greater than 0, that is to say p less than 1. But the case p equal 1 is also dealt with before. We established this before, that this is also divergent. So the case p equals 1, this is also divergent. It's also because of the integral test, because if we take the integral from 1 to infinity of 1 over x, right, when p equals 1, and it's not the power rule, but it's natural log of x between 1 and infinity, but in the limit, of course, natural log of x goes to infinity. So this will be infinity as x goes to infinity. So the divergence happens when p is, p is less than 1 here. When p is less than or equal to 1. When p is less than 1, or when p is equal to 1. So you can put together these in two basically big cases. And in the literature, this is called the p-series test, because you don't want to do these integrals one more time each time you encounter the a p-series. So the p-series test simply states that summation from 1 to infinity of 1 over n to the power p is going to be convergent provided that p is strictly less than 1 and divergent if p is greater than or equal to 1. So on the last page, we're going to finish up with some examples of p-series and some other examples that are suitable for the integral test. And then we call it a day, because when the p-series test is applicable, it's a very simple test to apply. The only issue is to recognize whether you have a series like this. And sometimes you need to do a little bit of algebra to figure that out, as I'll show you immediately. So stay tuned for the last page. All right, so before the examples that I want to mention at the end of the lesson today, let's mention a couple of two properties that really are inherited from properties of limits, and both of them are quite intuitive. So first of all, if you have the, let's see, if you have two series, let's say you have summation from 1 to infinity of an convergent and summation from 1 to infinity of bn convergent as well. So these are essentially like operations with convergent series, basically. If you have a sum of the two, so again we have these two series, both of them convergent, then the series that comes from adding or subtracting an and bn is also convergent. So you can break down, of course, the series into several pieces, and if each piece is going to be convergent, then of course the summation is also convergent. So you can add the series if you want, either as two separate sums or together like this. Or you can multiply by a constant, for example, an. So for example, you could have summation from 1 to infinity of some constant c times an, which is also convergent. C is a constant. Again, provided that summation of an is convergent. So the reason why we have these properties is that these constants can be pulled out of the summation, and then you can decide the convergence of what's left, or like I said, you can break it down into pieces like this. So let's put together, for instance, what we learned with the p-series. Let's say you have summation from 1 to infinity of 5 plus, let's see, n squared over 3 times n to the power of, let's say, 6. So if you look at this, you may think of a complicated problem, but this is just a combination of two p-series and then times a constant maybe. First of all, remember, so again, the question as always is whether it's convergent or divergent. Always check to see if the divergence test will tell you if it's divergent or not. So because this goes to 0, then divergence test does not apply. Remember, if it doesn't go to 0, the game is over. It means the series will diverge. If the term in the summation goes to 0, then you have to move on with other tests to see if it's convergent or not. But you should always check this limit because, again, this will be an easy way out if it's not equal to 0. How do you now figure out if this is convergent or not? Well, you got to do some algebra to see if it's made of pieces that can be analyzed separately. So obviously I can distribute the denominator. And then I do some simplifications here. So this is 5 over 3 times 1 over n to the power 6. And then plus, if I simplify n squared, this is going to be 1 over 3, 1 over n to the power 4. And based on the properties that I see above, I notice that this is actually, this breaks down into 5 over 3 times summation of 1 over n to the power 6 plus 1 over 3 summation from 1 to infinity 1 over n to the power 4. So it breaks down into constant times the series plus another constant times the series, but each is a p-series with p greater than 1. For this one, p equals 6, which is greater than 1. For this one, p equals 4, which is greater than 1. So by the p-series test, both will be convergent. And therefore, this is convergent as well because it's a linear combination of convergent series, right? So a constant times a convergent series is convergent. 1/3 times a convergent series is convergent. So then when I add up, is also convergent. This is just because of limits. Remember, an infinite sum is a limit. It's the limit of the partial sums. So whatever you learn from properties of limits still applies in this case. It's just a matter of recognizing whether that is whether it's made of p-series or some other series that you know. Be aware that p-series sometimes can be quite ugly in terms of the exponents. They're still p-series, which that means they are easy to analyze from the p-series test. So for example, let's say I have summation from 1 to infinity, and then I have, let's see, 3n plus 1 over square root of n. This is still a combination of p-series. You just have to write everything as a power of n. So square root of n is n to the 1/2. Break it down as we did it before. So if I simplify by n, I have 1 on the top, n over 1/2 minus 1 plus 1 over n to the 1/2. And this splits into the summation from 1 to infinity, 1 over n to the minus 1/2 plus summation from 1 to infinity, 1 over n to the 1/2. Now, both of these are P series with P less than or equal to 1, right? If it's 1 or less, then the series will diverge according to our theorem or our P series test. Incidentally, this one, the first one, is also divergent because of the divergence test, because n to the minus 1/2 is n to the 1/2, which is square root of n, and square root of n goes to infinity, which is not 0. So sometimes you can give the argument of divergent or convergent by more than one way, basically. It doesn't matter which one, as long as it's the easiest one you can find. And remember, when I wrote here, this is important to write in the homework exams and quizzes, or exams or homeworks, because this justifies or shows that you know how to apply the criterion or the convergence test. You don't just write divergent, you have to state the reason why you concluded is divergent. So here you could say, okay, it's a p-series test, p is 1/2, it's less than 1, and that's it. I can understand from this point that you're trying to say that because the test states that p less than 1 means divergent, therefore this is divergent. Since we are on the lesson of integral test, let me finish with another example. Sometimes the series, the integral test is obvious because the integral is obvious on how to compute. So for example, here we have a apparently complicated series, 1 over n ln of n to the power 2. But if I think it in terms of an integral, I recognize that that integral is doable. Maybe not the easiest possible integral, but certainly an integral that I should know how to compute, because it's just a u substitution. 1 over x ln of x squared. That means you could use substitution, u with ln of x. The new bounds of integration, let's see, if x equals 1, u equals 0, ln of 1. If x is going to infinity, u ln of infinity is also infinity, as a limit, of course. Technically you should say x goes to infinity, like an arrow here, but I would understand what you mean. So in terms of u, this will be the integral from 0 to infinity. 1 over u squared, and then 1 over x dx is du. The antiderivative is minus 1 over u. Let's see, 1 over, I should actually, I have to make it a little bit a small modification, because this won't be defined for at 1. It'll be improper at 1 as well. And I don't want to overcomplicate the matter here. Let's just go in for 2 to infinity, because it's not defined at 1. ln of 1 is 0. So let me just change this quickly. Say you have from 2 to infinity, and that means the lower bound will be ln of 2, and everything else is the same. And this will be limit as u goes to infinity minus 1 over u minus 1 over ln of 2. So this first limit is 0, and then plus 1 over ln of 2. So therefore convergent. The integral is convergent, which means the series itself is convergent as well. Okay, so I think that's it for today, and I'll see you next time.